Okay, nice to see everyone again. It's 5:02. We will get started. So once again, welcome to our fifth meeting. The topic today will be Introduction to Derivatives. Not Introduction to Derivatives because that was the last meeting. Basic derivative rules. So derivatives of basic functions and stuff like that. So before I get started, I was wondering if anybody had any questions on the homework for continuity. If you have any questions, please feel free to unmute and we will go over them. Okay. Yeah, no one has any questions? Okay.
I have a question, can you cover a bit of the basics? So because I forgot some of the classes.
Yeah. So in case you forgot to watch some classes, the class recordings will be posted on Google Classroom. So the recordings for the previous 3 classes are already posted on Google Classroom. So if you go onto there, maybe go onto the classwork tab. Here, I'm going to show. So I'm going to share my screen. If you go onto the classwork tab here, so on Google Classroom, you should have these 3 tabs. And the class recordings should be down here. They're also posted in the stream, but that takes a bit of a long time to scroll through. It's much easier to access them like this. So these are the 4 classes that we've had so far. And when this class finishes, I'll post that recording here as well. So if you need a refresher on some of the basic concepts, you can definitely watch those recordings. Yes. Okay. But I won't really spend a lot of time reviewing old material on this lesson because we kind of have a lot to get to. But yeah, that's definitely a good question, and the recordings are here. Okay, so if nobody has any questions on the continuity homework, we will get started with our presentation about introductory derivative rules. So we'll start with a really brief review from the last meeting about derivatives, because I feel like this is a very important part of calculus. And by the way, one more thing before I get started. Sorry about jumping about, but if you have any questions, I won't really be checking the private chat. So please unmute and ask them. Okay. So back to the review from last time. We talked about what a derivative is. So a derivative is the instantaneous rate of change at a point. So a tiny change in the value of the function divided by a tiny change in input. And last time we also talked about the derivative of a function with respect to the input at a certain point. We talked about that being equal to the slope of the tangent line to a function at a point. So remember, the tangent line only passes through a function once. And then we also talked about some derivative notation and the formal definition of a derivative. So we can write the derivative in either of these 3 notations. And this is equal to this limit right here. The limit as h approaches 0 of f of x plus h minus f of x over h. And the idea is that as a change in input h approaches 0, you have this tiny change in the function right here over a tiny change in input, and that's your derivative. One more thing that's new before we get started, I wanted to introduce this new definition of a derivative. This is basically the same thing as this one right here. It's also using the concept of 2 points that are infinitely close to each other, except that in this definition, the 2 points that were infinitely close to each other were x comma f of x and x plus h comma f of x plus h. Here, the 2 points that are infinitely close to each other are x comma f of x and a comma f of a for some number a. And this right here gives the derivative of a function. This is an alternative definition to this one right here. We could replace this definition, this letter a with h, but this is how it's most commonly written, with an a instead of an h. I don't know why, but that's just how it is. Okay, so this was a brief review from last time. At this point, does anyone have any questions about derivatives, what we learned about last lesson? Because you will need this this lesson, and last lesson was a very important one last Saturday. So does anybody have any questions? And once again, if you do, make sure to unmute yourself because I will not be checking the private chat. Okay. So in that case, if nobody has any questions, we will get started. So the first thing that I will say is, as a warm-up, find the derivative of f of x if f of x is a constant function or if f of x is a linear function. So a constant function is just f of x equals a constant. You can think about it as a horizontal line that passes through the point 0, c. That's just the graph of f of x equals c. And then there's also linear functions. Those are just lines. You have this slope, which is usually represented by m. You have a constant, which usually is represented by, yes? Okay. Yeah, so that's, I already got an answer in the chat about the correct answer, by the way. But I will give you 5 minutes anyway to think about this problem. I will pause my share screen. And when I think I have enough answers, even if 5 minutes have not yet gone by, I will talk about the solution. Okay. Oh, and yes, by the way, I forgot to say, when you're posting your solutions, just make sure that you private chat to me instead of private chatting to everyone, because if you private chat to everyone, then everyone can see. So yeah, anyway, but yeah, present your solutions within the next 5 minutes. Okay. And this time I will be checking the private chats, so please type them in the chat and not don't say them out loud, because I want to give others a chance to try this problem. Okay. So in about a minute or two, I will go over the solution. And by the way, if anybody wants me to go over the solution now, you can always say so. Okay, since I haven't gotten a lot of responses, I will go over the solution. Okay, so I'm resuming share screen. And the key takeaway, so first we noticed that this case of a constant function, right? A constant function is just a linear function with a zero slope. So this right here, this f of x equals c, is just a special case of f of x equals mx plus c. So we will deal with f of x equals mx plus c first, and then apply that to f of x equals c with m equals 0. So notice that when you have a linear function like this, right, the slope at a point is just that's the slope of the function. So in this case, the derivative is the slope of the tangent line, which I drew in blue right here. You can extend this line, but I didn't, so it doesn't block out the original function. So essentially, the slope at this point right here is also the same as the slope at this point right here or this point right here. And this is because it's a linear function. The slope doesn't change by the definition of a linear function. And so the slope of the blue line is the same as the slope of the red line, which is just m. So the derivative of a linear function is just the coefficient of x. For a constant function, the slope is 0. So the derivative of a constant function is 0 everywhere. So I got a lot of correct answers in the chat that f of x equals c, the derivative of that is 0. So this fact right here, that the derivative of a linear function is just the coefficient of x, that's a really important fact. Okay, so now we talked about lines, we talked about constant functions. What about curves? So typically, a couple of things that I want to go over before we move on to the more general discussion. Typically, when you have a function f of x, it also has a derivative function f prime of x. That is, the output of the derivative function f prime of x, which is denoted by f apostrophe x, as we went over in the previous lesson. The output of that function at a given input x is just a derivative of f of x at that point x with respect to x. For instance, for linear functions, this derivative function is a constant. For nonlinear functions, we can use the definition of a derivative to mathematically derive that function, that derivative function, as you will see me do in a couple of minutes. And then, as a quick note, I will sometimes be saying the derivative of f of x to denote the derivative of f of x with respect to x. So I will definitely be saying this because the derivative of f of x or f prime is much shorter to say than the derivative of f of x with respect to x or f prime of x with respect to x. So you will definitely hear me saying this if I haven't said it already. Don't be confused that we're dealing with another input. We are dealing with the input x for now. So those are a couple of technicalities that I want to get out of the way before we get started. And we will get started with a couple of derivative properties. So this may look intimidating at first, but what these two fundamental properties of derivatives are saying is that if you scale a function up by a constant, then the derivative of that new function at a given point is the same thing as derivative of the old function at that same point times the constant by which you scaled it up. So we will prove this property. We actually prove both of these properties using the definition of a derivative. But this makes sense intuitively. Basically, what this means is you can pull a constant in or out of a derivative. The second property is saying that derivatives are additive. This means that if you take two functions, add them together, and take the derivative function, that will be equal to the sum of the individual derivative functions. So sometimes a mathematician would call a function that satisfies these two properties linear. It's not a linear function. It means like it has certain properties that linear functions also have. But of course, the derivative function isn't always linear. That's just, a mathematical convention. But these are the two most important properties that you will need to know. And the fun thing about this is these aren't arbitrary properties. We will actually be able to derive these properties using limit rules and the definition of a derivative. So first, we will go on to this scaling property here. So to prove this, we go back to the definition of a derivative, which states that the derivative of f of x is equal to the limit as h approaches 0 of this thing right here. So f of x plus h minus f of x over h. And when we scale this function up by a constant, this limit, we just has a c in front of each of the f of x terms. We can pull this c out, and then we can pull this c out even more out of the limit. Again, this is a limit property that we derived in the lesson 3 lessons ago. So it may seem like a long time, but once again, these limit properties come back. We use them for derivatives. And then, of course, this thing right here, you will recognize as a derivative of f of x. So we basically just pulled the c out and we justified it mathematically. Okay. So now with a similar argument, I want you to prove this property here. Or actually, no, never mind. I don't want you to do that because I don't know how I will be able to understand to type like limits and stuff in the chat. It will be pretty difficult. So I will go over the proof here, but if you want, feel free to stop, like write the proof down on paper, because it always helps to go over these proofs by yourself. That is always very helpful. So the first thing we will do is, okay, this looks like a bit of a mess, but we first treat this sum of two functions as one single function, which it basically is. So we plug in x plus h into the sum of these two functions, and then we subtract the actual sum of these two functions. And then we divide by h, and that is the derivative. So then, of course, we can distribute this minus sign and simplify some more. And we can split this thing right here into two limits, like this. And once again, this is just basic algebraic manipulation of the numerator, and then using the fact that we can break a limit of a sum into a sum of a limit. So this is basically just how we got there, basic algebraic manipulation and limit rules. And then you will definitely recognize this as the derivative of f of x, and this is the derivative of g of x. So we just prove this property here. So like I said, these proofs may seem trivial, but it's very easy to jump over the mathematical proof when you are dealing with such simple properties. And it's really important to have a basic mathematical foundation for why all of the more advanced stuff that we will do later on actually works. Okay, so this one is the one that I want you to try to do. Using the previous two properties we derived, so c times the derivative of f of x equals the derivative of c times f of x, and that the sum of the derivatives of two functions equals the derivative of the sum of those same two functions. So now I want you to prove this property right here. So this basically, I'm going to pause my share screen. So this basically says that the derivative of a difference of two functions is equal to the difference of their derivatives. So pause, try to prove this by yourself, and then when you prove it, you type done in the private chat or in the public chat, but preferably in the private chat you type done, and then once I have enough responses, I will go over the proof. So once again, I'll give you 5 minutes to do this approximately. Okay. So I will give about a minute and then I will go over the proof. Okay. So sorry if this is a bit, oh, actually, no, there is more. Okay. So I will now go over the proof. It follows pretty easily from what we have already done. And the key thing here is to think of the negative signs as minus additions. So what do I mean by that? Well, we can rewrite this minus g of x as -1 times g of x. And then we can treat this -1 times g of x as a separate function and split it off. Right, this is by the second property that we proved, that you can split derivatives of sums into sums of derivatives. And then notice that this term right here is pretty much ready to go. And then this term has a -1 times g of x. -1 is a constant. By the first property, we can pull it out. And so there we have it. This is also a very basic property that you will probably need to know when doing calculus. And it's kind of important that you memorize these three properties that we just proved here without going through the proofs each time, because these are one of the few things in calculus that you will actually have to memorize. I'm sorry if that sounds I don't know, pretty bad, but that this is a very important operation that we will need for calculus. Okay, so with those three basic properties out of our way, let's think about some more complicated functions that we can differentiate. And by the way, if you hear me say differentiate, that means take the derivative of. So to take the derivative of something is to differentiate that function. So what if we try to differentiate more complicated functions, like f of x equals x squared? That's the most simple example of a quadratic function. So we talked about linear functions and constant functions, but what about quadratics? Well, here we once again use the limit definition. So if we plug in x plus h into x squared, into the argument of this function, we can expand x plus h squared. This is a basic rule in algebra, right? A plus b squared equals a squared plus 2ab plus b squared. No, we just use that rule here. And then notice that very conveniently, the x squared cancels out. Now we have this limit as a result. And notice that in the denominator, we have h, and in the numerator, all of the factors also have an h. So we can cancel all of that out. And basically, as h approaches 0, this plus h goes to 0. And so all that's left is this 2x, which doesn't depend on h at all. So the answer is 2x. So this is actually pretty cool. What this means is that the derivative of x squared at a certain point, so the slope of the tangent line at a certain point, is equal to 2 times the value of that input, which is actually pretty nice. So an example is, now that we know the derivative of just the lone x squared, we can actually figure out any derivative of any quadratic function. So for instance, if we have this derivative right here that we want to evaluate, the first thing we can do is we can split it up into a sum of many smaller derivatives. Then we can say that 7 is just a constant, so its derivative is 0. 5x is a linear function, so its derivative is 5, the coefficient of the x term. And once again, we have to pay attention to this minus sign. We're subtracting the 5 off. And then we can pull this 3 out of the derivative. And then using our previously derived fact that the derivative of x squared is 2x, we get that the final answer is 6x minus 5. So this seems like a pretty neat result. We can actually find the slope of a tangent line at any point along any quadratic function. Just take a moment to digest that, because I think that's a pretty neat fact. And once again, this means that at x equals 1, the slope of the tangent line to this graph right here is 6 times 1 minus 5, which is 1. Okay. So another thing we can do is not just find the slope of the tangent line, but we can find the equation. Once again, if we know the slope of the tangent line and we know one point that it passes through, then we can use the point slope form to find the equation of the line. So at the point 2, 4, there's a line that is tangent to this parabola, y equals x squared. And by the way, 2, 4 does lie on the parabola because 2 squared equals 4. So we have to find the equation of the line that is tangent to y equals x squared at this point 2, 4. Now, the slope of the tangent line is just the same thing as the derivative of x squared with respect to x at x equals 2. And then we already derived a formula that we can use for the derivative of x squared. For the specific function of x squared, its derivative is 2x. So what we can do is we can plug in x equals 2 into 2x. So at x equals 2, 2x is just 4. So the slope of the tangent line and the derivative is 4. So now we have already found the slope of the tangent line. We know that 2, 4 lies on the tangent line because the tangent line passes through 2, 4 by definition. So we have a slope and a point. We can find the equation of a line. We use the point slope form from algebra. And after some manipulation, we get that this tangent line has an equation of y equals 4x minus 4. This is actually a pretty neat example of what we can do with our new capabilities, since we can not only find the derivative at any point on any quadratic equation, but we can also find the slope of the tangent line at any point to any quadratic equation, which is pretty neat, actually, in my opinion. Okay, so now let's leave quadratics behind and enter the world of cubics. So f of x equals x cubed is a cubic function. And now a general question is, or a natural question is, what is its derivative? Well, we can do the same thing that we did with the x squared, plug it into the definition of a derivative. What we have here is we can expand this out, and this is the expansion for x plus h cubed. You can get this if you know the binomial theorem. You can get this expansion by yourself. I'm assuming everyone here knows what the binomial theorem is. It's basically a way to expand a binomial, so something plus something raised to the nth power. And so by the binomial theorem, this expression yields this. You can also multiply x plus h out 3 times, and you would get the same result. So then the x cubes cancel out, and we get this limit right here. And once again, all of the factors have an h in them. So then the h's cancel out, and we get 3x squared plus 3x times h, because the h squared turns into an h, and then plus h squared. So as h approaches 0, these last 2 terms go away because they're multiples of h. All that's left is a 3x squared, which doesn't even depend on the h. So we can just ignore the limit completely at this point and say that this is equal to 3x squared. So just like that, we found a general formula for x cubed. And now we can find the derivative of any cubic function at any point. So that's also pretty cool. We can extend into quadratics. So now let's see how much time I have left. It's 33. Okay. So now a quick challenge. I will give you maybe also 5 minutes to do this. Using our previous method, find the derivative of x to the 4th. So once again, try doing out the algebra, plug in x plus h into the function, and see how it comes out. And then when you're finished, please just type done and type your answer also. So if you want to type a power, remember you can type Shift 6. So yeah. Try to find the derivative. I will give you about 5 minutes to do so, and then we will go over it. Okay. So yeah. When you post your answers, make sure to post them in the private chat to me. Because then everyone can see your answer. And I don't know, that doesn't make it really fair for everybody. So the answer in the chat is correct. That is the derivative. If you are done, you can tell me. So I encourage you to keep working on this. Yeah. Okay. So the answer that is already posted in the chat is correct, but the most important thing isn't the answer, is the proof. So keep working on the proof, and then in about another 2 minutes, we will go over. Okay. Okay. So I will go over the answer now. So once again, we can plug it into the definition of a derivative, and we can expand however you want. You can expand this. I use the binomial theorem, but you can multiply it out. It's long, but it works. Then the x force and the x to the fourth here, they cancel out. All of the resulting factors in the numerator have an h in them, so the h's all go away. And then once again, the only term that does not have an h is the 4x cubed. all the terms that do have an h go away, and so the answer is 4x cubed. So now we can use our tools and expand them even more to functions of a fourth power. So x to the fourth, quartic polynomials. We can differentiate those now, which is actually pretty cool. We can keep doing this. We can keep doing this for x to the fifth, x to the sixth, and so on. But by now, let's develop a general rule for x to the n to get all of the derivatives down in one fell swoop. So here I'm going to write out the derivatives of all of the polynomial functions that we have studied so far. So x squared, x cubed, and x to the fourth. So if anyone notices a pattern, please just call it out, because I won't be checking the chat, or I will, but I might not get back to you as quickly as possible. So who knows what the pattern is here? Can you notice it? And once again, please just call out, raise your hand, or something like that. Okay, that is correct. So yes, Ria.
I think the pattern is that the coefficient is like the number squared. That's
Yeah.
the exponent. That's for the x, and the exponent of the x is just the
One smaller.
exponent minus 1.
Yeah, that's exactly the pattern. Very good. So already 2 people have answered about what the pattern is. That is the pattern. So what you do is you bring down the exponent, and so that becomes the coefficient of the derivative, and then the exponent of the derivative gets subtracted. So this generalizes actually to higher order derivatives. So if you have the derivative of, and by the way, so if you have the derivative of x to the n, where n is any number, not just 2, 3, and 4, then the derivative is you bring down the n, and then you subtract 1 from here. So it's n times x to the n minus 1. Now, this is really an important observation because this holds for all real numbers. So it holds for n equals pi. So if it was x to the pi power, it holds for x to the square root of 2 power. It holds for x to the negative 1/2 power, or even x to the 0th power. Any real number, n that you plug in, and that is the pattern. So right now we only have the tools to prove this for integers and for positive integers n. But when we get to more advanced rules such as exponents, derivative of exponential functions and stuff like that, product rule, chain rule, so all these advanced derivative concepts. So at that point, I will definitely talk about a proof of this more basic rule for non-integers n. But for now, we only have to prove the tools to prove this for positive integers n. But this works for any n. And what's crazy about this is that now we can find the derivative of any polynomial. Like, just think about this. Any polynomial that we are given, we can find the derivative with relative ease. So we can use this power rule. We can use the sum of derivatives equals derivative of sums. Constant times derivative equals derivative of constant times function. Right? We can use all of those properties, and we can find the derivative of any polynomial at any point. So once again, not just polynomials, but any power function. So we can find the derivative of x to the pi minus 5x to the negative 1/2 plus x squared. We can find the derivative of any power function. So this is actually pretty cool. So now I will prove this for positive integers, and this says integers, but it should say positive integers. We don't have the tools for even negative integers, but we will definitely have them later in the course. So we can do this right here. And this is just something basic called the binomial theorem. If you want to, if you don't know it, you can always look it up for more detail. But essentially what this says is that if you have two things that are added and raised to the nth power, what you get is the coefficient for each term is a binomial coefficient. It's n choose the number of the term. So for instance, here the coefficient is n choose 1, which is n. So these are like special coefficients that we use in math, but I won't be going into detail about them here. But this is the formula for the second term of any expansion that looks like this. And then the rest of the terms all have an h squared as a factor. So h squared times some polynomial. And then, of course, we can't forget the minus x to the n. Once again, the x to the n cancel. We get this right here. And then this simplifies even further. We have the h squared times some polynomial turns into h times some polynomial. And then this h goes away because h approaches 0. And we get the proof of the power rule. For positive integers, once again, that's all we can prove right now. So this actually gives us a really cool guide to differentiate a polynomial. The first step is to split the polynomial into many derivatives of a monomial. So in our 3x squared minus 5x plus 7 example, how we did this is we split it up into derivative of 3x squared minus derivative of 5x plus derivative of 7. Then the second step is to simplify the derivative of the constant and the linear term. Once again, that is just the derivative of any constant whatsoever is 0, and the derivative of a linear term is just the coefficient of x. So once you did do that, you pull the coefficients of all higher order derivatives out. Once again, we can do this by our derivative properties. And then we use the power rule and simplify. So for example, if we had the derivative of 3x to the 4th minus 5x cubed plus 8x plus 1, just any old random polynomial. First, we think about the derivative of 3x to the 4th. 3x to the 4th, that's the same thing as the derivative of x to the 4th times 3, which is 4x to the 3rd times 3, which is 12x cubed. And then we continue in this manner for all higher degree terms. So we get that this right here is minus 15x squared. This right here, that's just a linear term. It turns into plus 8. And the derivative of 1 is 0. So this is how a procedure we can do for any polynomial, or for the matter, any power function. So for instance, if this wasn't 3x 4th minus 5x cubed plus 8x plus 1, if it were like x to the e plus x to the pi minus x to the root 2 plus 8, for instance, we could find the derivative of that too. Okay, so this is it for this lesson. Now I will, how much time do you have? Okay, we already passed time actually. Now I will recap. So the derivative of f of x is the function f prime of x, whose output is the derivative of f of x at that input. So basically, that any function, almost any function, has a derivative function. It may not be defined at all points, but it might. Usually, for most of the functions that we study in this course, it does exist, and for most of the derivative problems that we study in this course, you will be asked to find it. So the derivative of a linear function is the function's slope, and the derivative of a constant is 0. So this is like really important. Always remember that. A lot of students commonly make the mistake that the derivative of a constant is just that constant. For some reason, they like automatically forget the derivative standing in front of the constant. That's not the case. If you want to visualize it, think about the constant being a horizontal line. The slope of a horizontal line is 0. So if you want, that's how you can think about it. But that's an important rule that you have to remember pretty much. Okay. And then for more advanced derivatives, we can use the definition of a derivative to find f prime of x. And for a derivative that is a sum of many derivatives or a constant times some other function whose derivative we know, we can use these two properties, which we proved using the limit definition. So once again, these are also two very important properties. Once you start being more advanced at calculus, you will basically know these properties automatically. But at first, it might take some time getting used to this. So yeah, so that's why we prove these properties. That's why I put so much emphasis on all of this. And then, of course, we have the power rule, which has for any real number n, the derivative of x to the n with respect to x is the same thing as n times x to the n minus 1. And we can use this power rule to differentiate any polynomial or other power function. Okay. And once again, derivatives are really important for any branch of science, all of calculus, all of higher level math. So all of this is the fundamentals of higher level math and science. So it might seem a bit arbitrary. It might seem that we have left the world of actual objects and entered a lot of hypothetical stuff, but this is really important. So it's important that you as you memorize these rules, know the proofs, and yeah. Okay, so we are done for today. Does anybody have any questions about the lesson, about derivatives, about limits, about continuity, about anything we've studied so far? No? All good? Okay. So in that case, I will post the homework on today. I should post the homework. Yeah, you're welcome. Great job to everybody who participated. Keep up the good work. And yes, the derivatives homework is due tomorrow. If you have trouble on any problem, email me, write a post on Google Classroom. If you think that this will help you or the rest of the class. Okay. Thank you so much, Henry, for your feedback. It's really appreciated. Okay, and good job to you too. You did really well today. And okay, so everybody did really good today. Thank you so much for coming, and I'll see you tomorrow. Yeah, tomorrow for our class on more advanced derivative techniques. Okay, have a good day.